One of our main purposes in section 1.2 is to be able to multiply polynomials together. Before we do that, however, it's important that we understand the rules of exponents. So let's take some time to carefully review the rules of exponents. Use the following rules to simplify expressions with exponents. Assume that a is not equal to 0 and that m and n represent real numbers. Now, just to remind you of the terminology, when you have an exponential expression, the number on the bottom, the a in this case, is what we call the base, and the number in the superscript position is what we call the exponent. So if we are multiplying two exponential expressions with like bases, we're going to apply what we call the product rule. Notice here we have like bases a and a. So if I'm multiplying, and let me correct a typo here, a to the m times a to the n is going to be equal to a to the m plus n. In English, we would say when multiplying like bases, we add the exponents. Similarly, when dividing like bases, we subtract the exponents. So a to the m divided by a to the n is equal to a to the m minus n. When dividing like bases, subtract the exponents, top minus bottom. Also be aware that anything raised to the 0th power is equal to 1. Sometimes your brain's going to want to look at that and think multiplication and call it 0, but anything to the 0th power is equal to 1, and you can certainly verify that with your calculator. Next, we have the rule called power to a power. Notice how this one is different from the product rule. In the product rule, you have two separate bases. In the power rule, I have a single base raised to another and then successively raised to another power. So when raising a power to a power, we multiply the powers, whereas when multiplying like bases, we add the powers or add the exponents. Next, we have a product raised to a power. If I have more than one factor raised to an exponent, then it is legal to distribute that exponent. So we would end up with a to the nth power times b to the nth power. Notice you can distribute an exponent across a product, but it is illegal, make sure you get not equals here, to distribute an exponent across a sum. When we raise a quotient to a power, we can also distribute the exponent to the numerator and the denominator. So the fraction a over b to the nth power becomes a to the nth power divided by b to the nth power. And when we have negative exponents, that just indicates a change in position. So when raising a to the negative nth power, that negative signals to us that we need to move the exponential expression to the opposite place in the fraction, in this case the denominator, and then change the sign of the exponent. If the negative exponent is in the denominator, that signals we need to move the entire expression to the numerator and again change the sign of the exponent. So these are very important rules and we'll use them all semester. So let's practice applying these rules on a few examples. Simplify the following expressions using the rules of exponents. Write the answer with positive exponents only. So in our first problem, we have 3x to the 4th power times negative 5x squared. Ultimately, we have four factors here. 3 times x to the 4th times negative 5 times x squared. And because multiplication is commutative and associative, we can multiply those factors in any order. So let's choose the most convenient order. That is, let's multiply the constants together first. 3 times negative 5 gives me negative 15. And then we'll multiply the variable parts together next. X to the 4th times x squared. Notice we're multiplying like bases, so we need to add the exponents. So we end up with negative 15x to the 6th. On our next example, we're going to be dividing exponential expression. 12x to the 9th y to the 4th divided by 6xy. Now the first thing I'm going to do is reduce the numbers. 12 and 6 have a common factor of 6. 6 divided by 6 is 1, and 12 divided by 6 is 2. So our resulting fraction here is going to have a numerator of 2. Then notice we have like bases that we're dividing. X to the 9th divided by x to the 1st. We can simplify by subtracting the exponents. And y to the 4th divided by y to the 1st, again, we can subtract exponents. So we end up with 2x to the 8th, y to the 3rd. We have only positive exponents in our answer, so we are finished simplifying. Now, example C looks a little bit complicated, but notice we have a big entire base with lots of different operations all raised to the 0th power. So it doesn't really matter what's going on with the base. When we raise it to the 0th power, we get 1. Anything to the 0th power is equal to 1. So that one's a pretty easy one. Next one, we have the product 2x cubed y to the 4th raised to the 2nd power. So we have the product of several factors raised to the 2nd power. So we need to distribute that exponent to each factor in the product, including that coefficient. So don't forget about that. So when we distribute the outside exponent to each expression, we end up with 2 squared. Now I'm going to take the original x cubed and put that in parentheses and then distribute the outside exponent to that factor. And I'm going to do the same thing with the y to the 4th here. So each factor, each original factor, received that additional outside exponent. Then we can simplify. 2 squared is 4. Notice next we are raising a power to a power, so we need to multiply the powers. X to the 3 squared would be x to the 3 times 2, or 6. And y to the 4th squared, we're going to multiply the powers to get y to the 8th. So we end up with 4x to the 6th, y to the 8th power. Okay, so far so good. Let's move over here to example E. Now on example E, we have a quotient raised to a power. So I need to distribute the exponent to both the numerator and the denominator. And the denominator has more than one factor, so we're going to distribute that to each factor in that product. So we're going to end up with, on the top, x cubed raised to the 4th power, and in the bottom, 2 raised to the 4th power, and y squared raised to the 4th power. So every factor got that outside exponent. Again, we have the situation where we're raising a power to a power. So we need to multiply these two powers. So x cubed raised to the 4th power would give me x to the 12th. 2 to the 4th, meaning 2 times 2 times 2 times 2, would give me 16. And y squared to the 4th, multiplying the powers, would give us y to the 8th. On the next example, we have 5x over 12 to the negative 2. Let's begin with 12 to the negative 2 in the denominator. Remember, when you have a negative exponent, we're going to make 2 changes. We're going to move the entire expression to the opposite place in the fraction and change the sign of that exponent. So that 12 squared is coming upstairs to join the 5x. We'll have 5x times 12 to the positive 2. Again, the 12 is out of the denominator, in the numerator, and we changed that negative 2 to a positive 2. Then we can execute 12 squared to get 144, and 5 times 144 gives us 720. So our final result is 720x. Next, we have a big quotient to simplify. The first thing I would do is simplify our numbers. Between 8 and 16, we have a common factor of 8. 8 divided by 8 is 1. 16 divided by 8 is 2. Then we have a combination of positive and negative exponents. So I'm going to move things around a bit. Anything with a negative exponent, I'm going to move to the opposite place in the fraction. So this x to the negative 2 is moving downstairs. So there's already an x down there. Now we're going to multiply by x squared. For now, I'm going to leave the y's where they are. I have a y cubed in the top, y to the 5th in the bottom. And then let's observe z to the 0th is equal to 1. And then we're going to move z to the negative 2 upstairs. So we have 1 times z squared. Next, we have a couple of like bases that we're multiplying here, and we have a couple of like bases that we're dividing here. So, multiplying like bases in the denominator, remember you can imagine an exponent of 1 right here. So 1 plus 2 gives me 3. Then we have y cubed divided by y to the 5th. Now notice there are more y's in the bottom than there are in the top. So the leftovers are going to end up in the bottom, right? So y cubed divided by y to the 5th, I'm going to execute 5 minus 3 to get y squared. And then we have a leftover z squared in the numerator. If you want a little more explanation on what's going on with the y's, notice I have 3 y's on the top, I have 5 on the bottom. So if we expand those exponents, that's what it looks like. 3 of them are going to cancel, and that's going to leave y squared in the denominator. For our last example here, I would begin by simplifying what's inside parentheses first. So executing the negative exponents, we're going to move the x to the negative 2 downstairs, and we're going to move y to the negative 4 upstairs in the numerator. So that's going to give us a 3 in the numerator, y to the 4th, there's already a y cubed that's up there, and x squared is moving downstairs. We still have this exponent negative 2 on the outside to deal with. But before we deal with that, let's go ahead and multiply these like bases by adding exponents. So we'll have 3y to the 7th over x squared. Now next, if you wanted to, you could distribute that negative 2 outside exponent to each factor in that quotient. But when we distribute that negative exponent, it's going to make each factor switch positions in the fraction. So to make it really easy, if you have a fraction raised to a negative power, simply invert the fraction and then change the sign of that outside exponent. Then we can apply that exponent to every factor in the quotient. So in the top we have an x squared, it's going to get another exponent of 2. In the bottom we have a 3, it's going to get squared, and y to the 7th squared. And remember when we have a power raised to a power, we multiply the powers. So we end up with x to the 2 times 2, or x to the 4th. 3 squared is 9. And y to the 7 times 2 gives me y to the 14th. So we end up with x to the 4th over 9y to the 14th. So those are basic rules. They can be applied in various orders, but they will be important for the rest of the semester, so take some time to master those rules.